thanks a lot for showing up. And thanks a lot. I think this is a really good seminar series. So before term started, I committed myself to giving this. Obviously, knowing full well that it was going to be in the middle of the term and I was going to regret having committed myself to giving this. But I'm knowing that by tomorrow I would be very glad that I have. So I'm glad I'm here. So this is the title that I put in the email that I think was sent around. And I guess this is the title that will appear on the website. I wanted to have a different title. This is the title I really wanted to have. But what I really want to call this talk is why I don't care if no one ever builds a quantum computer. But then I thought that maybe having a title that basically undermined the entire basis of funding for my field, having that on the web maybe wasn't such a good idea. So I chickened out, but this is the real title of the talk. So I hope by the end of the talk to have persuaded you of that title, why you shouldn't care if no one ever builds a quantum computer either. So I work in quantum information theory. Quantum information theory is one of the youngest fields of theoretical physics, which means it's about 20, 30 years old. And it's really a field that sits somewhere at the intersection between physics, maths, and computer science. Quantum information theory really sits there. For me, that's kind of what I think is what I find most exciting about the field. And really the talk today, what I'm going to try and tell you today is really about exactly why it sits in the middle there. But I'm going to get rid of this, because the mathematics in quantum information theory is really, it's not that difficult. You can teach quantum mechanics to people who just have GCSE level maths. And all of the exciting stuff doesn't require extremely heavyweight maths. However, it does require a few more than just one talk. So, and since I know this is I don't know how broad this audience is, but I'm going to assume it's broad enough to include some arts, humanities people as well. Which means I'm going to just get rid of all the maths from the talk and I probably won't have any equations. So really I'm going to be talking about how quantum information merges these two. And in some ways that's the most exciting part, because maths and physics, everyone knows that physics teaches maths, and that physics has something to say about maths sometimes as well. There's a connection between the two. But this is in some ways this is the new contribution, if you like, to the field of quantum information theory. Good. So this is what I need to tell you about. So in order to tell you about what quantum computers tell us about physics, I realized when I was preparing slides that I set myself kind of a mountain to climb. So first thing I need to do is to tell you about quantum computing first, before I can tell you about what quantum computers tell us about physics. But in order to tell you about quantum computing, I need to tell you first about computing, and I need to tell you about quantum mechanics. So hopefully you're free all night, and hopefully not. So I'm going to explain what computation, quantum mechanics, quantum computing are, and then hopefully I'll have time to tell you about how there's any relationship between, in particular, this quantum mechanics and quantum computing and physics. So that's where I'm going. So computation. Let's start there. You probably have a pretty good idea of what computation is. So this is let me give you a slightly more precise idea of what computation is without being certainly precise enough for this talk. So we can always think about computation as being some form of circuit, which takes some bits. And these bits go through the circuit and get manipulated by gates in the circuit. These bits there might be a number we're doing some computation with, there might be your latest paper that you're trying to edit. Doesn't matter, we can always represent everything as bits. And these go through, they get manipulated by the circuits, they flow through so that we can represent this as it's going through the circuit from left to right. These bits here then go through this gate and get merged together and you get some output. Okay, I don't really care about the details, this is just some schematic. But for this talk, computation is something that does this. It takes a sequence of bits and it manipulates them to get some output. That's enough. That's if you understand computation on that level, that's plenty for this. Okay. Good. So that's computation. That was easy. Let's move on to quantum mechanics. Actually, there's a lot I could say about quantum mechanics. I could talk about, for hours about it. Give me a 8-hour lecture course and I could teach you quantum mechanics even if you're not a mathematician or a physicist, even if you're doing art history. I would like to take on that challenge someday. But for today, you don't actually. The one thing you need to know about quantum mechanics is superposition, and many of you probably may well have heard of Schrödinger's cat. It's not clear whether Schrödinger ever had a cat. People have actually tried to look into this, and no one's really managed to find out for sure. But if Schrödinger did have a cat, he clearly didn't like it very much, because what he thought about was, let's imagine putting this cat in a box, and we're going to sex things up so that the cat, well, the way he describes it, he has a vial of cyanide in the box, and then he has a radioactive particle, and he has a Geiger counter, and then the Geiger counter is attached to a hammer that, if the Geiger counter triggers, the hammer drops, smashes the vial of cyanide, and the cat gets killed. Back in the 1930s, there weren't any ethics committees that you had to get this passed, so it was easier. The point is that this atomic radioactive decay is a quantum process. Our best understanding of physics is that that is something that's purely random. There's no way of predicting when a radioactive particle is going to decay or not. It's not just that we don't know, it's that it's fundamentally the rules of quantum mechanics don't. They say that the particle can be in a superposition of having decayed and not decayed at the same time. And it's not until you look at it that you discover whether it's decayed or not. What Schrödinger said, is that, if quantum particles can be in this strange superposition of being two things at once, then what happens when we break the vial of cyanide, depending on whether which state that particle is in, whether that atom has decayed or not, then the cat is going to end up in this quantum superposition of being alive and dead at once. And Schrödinger came up with this thought experiment, this Cubitt experiment, really to illustrate the absurdity of the mathematics of quantum mechanics. I mean, his point was that there's something, this can't be the whole story. Turns out, nearly, 90 years later, we really believe that this is what's going on. It's never been tried on cats, but we have done experiments on particles, all kinds of quantum particles. They really do seem to be able to live in this strange thing where they're both alive and dead at once, or they're in one location and another location at once, and it's not, and there's no way. It's not just that we don't know which location they are. It's not that we just don't know until whether the cat's alive or dead. It really is somehow both or not, and neither at once, until you look at it. And as soon as you open a box and look inside the box, then suddenly the cat is either alive or dead. And since I didn't get ethics approval for this experiment either, luckily for me the cat's alive, so I'm going to get away with this experiment. I could give a completely different talk on why we actually believe this completely absurd thing, and we've been forced for the last 100 years of one of the greatest theories in 20th century science, involving some of the greatest scientists, and we've been forced to accept this completely bizarre conclusions. Mathematically, this is completely trivial. There's nothing particularly. If you know what linear combination is, we're just taking a linear combination of alive and dead states. Nothing is. But what does it mean physically? People are still arguing about this. Nonetheless, we've measured this. We can experimentally see that this is what's going on. So as I said, I could give you a whole talk about that and the evidence for that and why we really believe this. But that's not what I'm going to talk about today. So I'm going to assume you're going to trust me that quantum mechanics is correct, and you can really, until we look in the box, this cat is in this strange superposition of being alive and dead. And all you need to know about quantum mechanics to understand what I'm going to talk about is to accept the fact that that's possible, and that's what really happens. Not necessarily to cats, but if we take atoms or electrons or photons and put them in superposition states, they can really be in two states at once. Until we measure them, and then they collapse. This is what happens with a subatomic particle decaying. It's in a superposition of having decayed or not until we look at it, at which point the universe decides whether it actually decayed or whether it didn't. It is as strange as it sounds, and which is why you really need, at the end of the day, even the people working in the area understand it through mathematics and not through some physics intuition. Some people would argue that it's simply our brains are not built to understand what goes on at the quantum scale because we never experience it directly. So, but anyway, there's people in the philosophy department who have spent years arguing about that. I'm enough of a physicist still to just say, okay, that's what it actually does. And what quantum information theory does is says, okay, all of these bizarre effects in quantum mechanics, including others that I'm not going to talk about today because I don't need to, like entanglement, which is closely related. Instead of thinking of these as some strange, bizarre phenomenon, quantum information theory turned this on its head and said, okay, we've got this strange, bizarre phenomenon that happen that don't happen in classical physics. Can we use them to do something useful? That, in some sense, is the question at the heart of quantum information theory. Can we do something useful with these bizarre quantum effects? Good. That's all you need to know about quantum mechanics. You need to buy that, and then, as long as you're prepared to swallow that for the next hour, you know enough quantum mechanics to understand quantum computation, or at least to get some sense of what's different about quantum computers. So, unfortunately, the pioneers of quantum information theory misspelled the word for qubit. They spelled it with a Q. Obviously, it was supposed to be spelled with a C and an extra T in the end, but they messed up. We're now stuck with this misspelling, so unfortunately, I know maybe I have to change my name, misspelling my name. This is a qubit. It's just like the cat in the box. We put a bit, which is either 0 or 1, but we put it in a quantum superposition, so it's actually not just 0 or 1, but it's both at once. And it's not that we don't know what the value of this bit is in the box, it's that it's both in some weird quantum state of being somehow both at once until we look at it. And that is what a quantum bit is. That's what a unit of the smallest piece of quantum information analogous to the classical bit is. It's just a bit in superposition in a box. So what happens if we feed these quantum bits through our computing, our circuit? Just a line there. Well, this circuit can operate on these quantum bits just as it would as if they were classical bits. But now, if we've got, in this very simple circuit, I've got 3 quantum bits going through this. So this one is in both 0 and 1 at the same time. And this one is in the superposition of both 0 and 1 at the same time. And this one is in the superposition of 0 and 1 at the same time. The overall effect of this means that these 3 bits that are going through my quantum circuit, well, they could be 0, 0, 0. But there also could be, at the same time, they're 0, 0, 1, and they're 0, 1, 0, and 0, 1, 1, and 1, 0, 0, and 1, and all 8 possibilities at once. Okay, it multiplies up. Right? This is either 0, 1, and this is independently or both 0, 1, and this is independently both 0, 1. So what we've got now is all of the possible inputs to this circuit at once, instead of just one at a time. So it's like we have this whole circuit as it processes this quantum data. Remember that these are qubits, they're in a box, we're not looking at them. So they stay in this superposition until we open the box and take a look. So they're in both states at once. It's like having the whole circuit, having many copies of the circuit, all at once, each one processing a different value of the input. But instead of actually having 8 copies of the circuit, we've just got 1, and it's doing all of this at once. Because each of these bits is in both possible values at once, and then the output of this gate here, well, it will be the effect of, if this was 0, what would happen to this bit if it was 0, in superposition with the other possibilities. Can anyone see the problem with this? How do you measure the output? Right, this is great. I've now just managed to do my computation. So it's like, I've written every possible scientific paper all at once, and edited it all at once, and now I've written every paper that could ever possibly be. The only annoying thing is that as soon as I open this box and look at what the output is and read that paper, it just chooses at random which one it's going to be, and it's probably going to be gobbledygook, right? Or we've computed, we've computed some problem, or we've computed every possible answer, and somehow encoded in this quantum state, if only we could extract the information, is all of the answers to every possible input we could have put into the computer. But the problem is that just like the cat decides when we open the box, the universe randomly decides if it's going to collapse into being alive or dead. The quantum computer, if I do what I've just described, will randomly pick one of these to collapse into, and then we just get one answer. And now we've done nothing better than classical computing. We've just picked a random input to our computer and got some output. So at best we've got one input, which may or may not be the one we wanted, and we've got the corresponding output. And now if we can do this 8 times, and well, do it a few more than 8 times, then with high probability we will actually get each of the answers out, but we've done no better than classical computing. We might as well just have done each classical input separately, got each of the answers, written them down, and it would have taken just as long. So this is half of the story of quantum computation, and why quantum computing can do more than classical computing. It is true that all quantum algorithms essentially start by doing this, but you have to do something cleverer than just measure the output. You have to measure the output cleverly. And that means you don't just look at what came out of what the computer spits out. You process that in some way so that you can extract some global information about the answer. Maybe you can extract, are there more ones than zeros? Do more of the answers have 3 ones than 3 zeros, say? That kind of global information, if you're clever, you can, for certain problems, you can find ways of extracting information about it. And then you really do get an advantage over classical computing. I don't need to talk about any of that, because for this talk, it's enough to know that you can compute in this, have a superposition of all of these different computations going on at once, and that is half of the story of what's behind quantum computing. There aren't very many if you're clever about how you do the measurement, some problems you can find clever ways of doing it and you can get some useful information out. Sometimes you can't. There are some problems where this gives you no advantage at all. You might as well use a classical computer. There are a small handful of problems where quantum computers give you a huge advantage. But there are only a handful of problems that we know of. One is factoring numbers. If I give you a very large number and ask you to find its factors, I give you 15 and you have to find that that's equal to 3 times 5. That problem is sped up, as far as we know, exponentially. It becomes exponentially faster on a quantum computer. Obviously, for 15 is not very difficult, but they give you a really huge number and ask you to find its factors. That problem is, as far as we know, very difficult to solve. The best thing you can do is see if it divides by 2, and then see if it divides by 3, and then see if it divides by 4. Actually, you can skip 4 because you've already tried 2, so see if it divides by 5, see if it divides by 7, etc. And that takes a very long time. Quantum computing can do that exponentially faster, as far as we know. And we hope that the problem is difficult on a classical computer because all of internet cryptography, when you buy something on Amazon, it's relying on the fact that that problem is difficult. If that problem was easy, I could get your credit card details and buy some very expensive academic textbooks off Amazon with your account. If someone ever builds a quantum computer, then we're going to,
so when you say most of the problems quantum computers are not going to be much efficient than classical computers, is it because it's fundamentally like that, or we just don't know the algorithm?
We don't know yet. So, we don't know. So there are some problems where you can prove that the quantum computers are not going to help. There are some problems where you can, and there are a whole load of problems where people are working very hard to see if they can come up with clever ways of exploiting quantum mechanics to speed them up. But it's not, you don't get it for free from this because of this collapse when you measure the output. You have to do something smarter on the output side than what I'm doing here. And that's the hard part. That's the genius of Peter Shaw with his factoring algorithm, was essentially not the part of like, let's do everything all at once in superposition, but how can I extract something useful from that at the end? One thing that, generally, I mean, this is not the topic of the talk, but briefly, why might you care about building a quantum computer, even if I claim that I don't? There's one thing that quantum computers will be extremely good for, and that's simulating quantum mechanics. It's not very surprising. It sounds stupid, but it's actually not, because I mean, almost 50% of theoretical physics struggles with the problem of trying to understand large quantum systems, collections of atoms in a material, many body problems in quantum problems. For example, we have a good idea we have a good guess for what is the explanation of high temperature superconductors. Unfortunately, no one can actually solve the model. We've got a model, but we can't figure out if that really does correctly model high temperature superconductors or not. There's a good guess for what the model might be based on physics, but no one can prove that it actually does give you high temperature superconductivity drops out of that. If you had a quantum computer, you could simulate that on a quantum computer and check. It's a bit like, you could just, every time you want to try a new wing shape for an aeroplane, you could build an aeroplane and see if it flies. But it's really useful to be able to model it on a computer and tweak parameters and see if it's going to work before you send someone up in it. There's a huge advantage to being able to simulate things on a digital quantum computer rather than just build a material and measure it. For example, you take a sample of material, it's really difficult to measure like what's going on to individual electrons. On a computer, if you're simulating it, you can of course try to not measure them, but you can just, that information is there in your quantum computer and you can probe it. So that, a lot of people argue that is the killer application of quantum computing. But there are others, there's factoring, it speeds up almost every hard problem by a small amount. if you want to know more about that, you can ask me at the end of the talk, because I want to get on to why you shouldn't care about that. Okay, that's a flavour of why quantum computers are different. Okay, there's something I forgot from this outline. I better tell you what physics is as well. So let me try and tell you what physics is in time. I've just drawn us some strange set of stairs with some slope in it. I'm a theorist, right? I get to draw silly diagrams and wave my hands and pretend that I'm doing some real science and just write down some equations, whereas real physicists have to actually do some experiments. So this is in a cartoon and it is less frivolous than it sounds. This is all of physics is kind of captured by this, or at least if you know it. So here's some physical system. I'm going to look at the energy of this system when I have it in different configurations. So if I put a ball on that top step, it has some energy. Let's draw a line with that energy. If it's slightly lower down, it's got a slightly lower energy. And I can plot all of this. If it's there, well, there's a whole continuum of different energies it could take as it rolls down that slope, and so on down to the bottom of that. And I can plot, if you like, the different possible energies, the different possible configurations of this system have. Those of you who do know physics know that I'm sort of glossing over a lot of things here, but not that much. This thing that says what does each configuration of my system, what energy does it have, this has a fancy name in physics. It's called the Hamiltonian of the system. Turns out that that's everything you need to know about the system to understand its entire behavior. If you know the Hamiltonian of the system, you know that for each configuration, what energy that configuration has. From that, you can derive everything about how the system behaves. That isn't complete information about the behavior of the system. So fundamentally, all of physics is concerned with Hamiltonians, or the energies of different configurations of the system. That doesn't change that much in quantum mechanics. If we have an atom, it probably looks closer to the kind of things you may well have seen. We have an electron around a nucleus, and it orbits. It's in that orbital. It has some energy. It can jump to a higher energy level. That gives it configuration with some other energy. There's also this configuration with that energy. Or the electron could escape from the atom, and then if it escapes, then it can take a continuum of different energies, and its velocity it can take any velocity. Whereas when it's confined to the atom, as I'm sure you know, the energy levels have to be discrete. So again, this is sketching the Hamiltonian of this system. So the energy of the different possible configurations of the system. Already from that, there was a huge amount. I mean, that's the beginning of quantum mechanics historically, because it's the fact that these energy levels were discrete and that you saw this corresponded to, if now the electron does jump between levels, well, it has to lose or gain energy. It either emits or absorbs a photon, and you see sharp lines in the spectrum of the light coming from the sun. So we learned a lot from the Hamiltonian system, from the energy of its configurations. In fact, as I said again, that actually gives us the complete description, because from that we can derive what the system will do if we started in any configuration. Good. So physics is all about, modelling a physical system is all about trying to write down its Hamiltonian. Here's an example of an energy landscape, schematically of a Hamiltonian, where we can actually learn something about the behavior of the system just looking at how the energy of its different configurations. Imagine we take this system and I try and, abstractly representing the system. This isn't some configuration, it's not necessarily all running downhill. Let's start it with that energy, so with the high energy, and we're going to cool the system down. What does cooling do? It removes energy from the system. So let's cool this down. Well, we can cool it down to that point, and this system is just going to slide down in energy, and we're going and get to this point. But now, if we try and cool it further, there's this hump it can't get over, right? Because it's got too little energy to jump over that hump. So we can try lowering it, cooling the system further, but actually it's going to get stuck there for a long time. We can make this mathematically precise. But the point is that systems that have this kind of energy landscape, we expect that when we cool them, they're going to get stuck in some metastable state, some state where somehow it gets very difficult to cool them down any further than that because of this barrier. And systems like that, an example of such a system is glass. Glass is a system that spends all of its time in a metastable state. If you take glass and cool it down, nothing much happens to it. But the lowest energy state of glass would not be this. It would not be glass. It would be a crystalline substance, because glass is a chaotic, a slightly disordered system. So glass is an example of something that has an energy stand state that looks something like that. It gets stuck as we cool it down. Again, we're learning a lot about, you can see that we get a flavour of the fact that we can learn essentially all of the physics of the system once we understand how the different configurations of the system, what energy they have. Okay, that was a very brief overview of physics. So now you know what computation is, you know quantum mechanics, you know how you can use that to do quantum computing, and now you know what we're interested in physics. So let's see how it goes. So manage that in about half an hour. So now I get to the real topic of the talk, which is to try and explain what on earth does all of this, which is about computing things, have to do with understanding the behavior of physical systems. Are there any questions? Any questions that aren't Toby or really even the email pictures of physics are embarrassing? Okay, so what do quantum computers tell us about physics? Even if one manages to build it. In some sense, this is probably conceptually the most important slide of the whole talk. There's a old result by Alonzo Church and Alan Turing, who in the beginnings of the whole field of computer science, they proved is not quite the wrong word, but they stated this as a sort of as a theorem or as an axiom that any reasonable model of computation you could ever cook up could be simulated on the computers that we know and love and that we use. Actually, Turing was talking about a different model of computation at the time. He was talking about Turing machines, which are a very simple model of computation. But what Church and Turing asserted was that pick whatever model of computation you like. It doesn't matter. What it can do is the same as what any other model of computation can do. Why is this so? Well, we'll see in a moment why this is actually, in some sense, this is why there's a connection between computation and physics. But this is formulated in this formulation was maybe took until the 1960s for people to crystallize that out of the results of the early pioneers of computer science. There's a stronger version of this, which says that, almost the same thing, and this goes by the name of the strong Church Turing thesis nowadays. It says that any reasonable model of computation can be simulated efficiently by a classical computer. In other words, if your state-of-the-art laptop can solve something in half an hour, then if you did it on a Turing machine with a piece of ticker tape and a pencil reading and writing on it, it wouldn't take that much longer, and making that mathematically precise. It just says that it doesn't take exponentially longer. Okay, maybe it takes a factor of 2 longer, or maybe it takes a factor of 1,000,000 longer, but it doesn't take. But if you double the size of the problem on your computer that you give to one computer, the time it takes on the other computer. Sorry, I shouldn't say that. If you just make the problem on one computer, you increase the length of the problem by 1. You add 1 bit to the problem. Then on your other computer, your slower computer, the length of time it takes won't double. It'll just increase by some linear factor, some constant. So basically, it just says that all computers, if you don't care about actual really doing this, but if you're how much computational time it takes to solve a problem doesn't grow too much faster on one computer than on another computer. And so from a theoretical standpoint, whichever model of computation you take, it's going to be equivalent up to constants that theorists don't care about. And if you're in practice, you would certainly care So this is a later formulation of something which has the name the strong Church-Turing thesis. It basically asserts that we understand. We can take our favorite model, simplify it, abstract model of computation. We're not missing anything. Turns out that we were missing something, or at least a lot of this is conjectures that most computer scientists and mathematicians believe that aren't strictly proven. But these days, people have now started calling something an updated version of the quantum Church-Turing thesis, because we saw the classical. I told you that quantum computation, you can do some things that you simply can't do classically, and sometimes you can use this to your advantage to do things much, much faster than you could classically. That would violate the strong Church-Turing thesis, because if we're right, a quantum computer can't be simulated efficiently by a classical computer. It doesn't violate the original Church-Turing thesis. You can simulate a quantum computer on a classical computer. Remember my box with all of the circuits in superposition? Well, instead you just do each one at a time. It takes a long time. Instead of having to do one computation, you'd have to do, in my simple example, 8. Why? Because there were 3 bits, so it's 2 to the power of 3. You can see now if I increase the number of bits in my circuit, each time I add a bit, I'm doubling the amount of time it would take to simulate that. But the original Church-Turing thesis says nothing about how long it takes. It just says, can I simulate it, even if I'm prepared to wait long enough. But the strong Church-Turing thesis asserts something stronger, which is that you don't lose anything. You don't lose too much. Quantum computing seems to violate the strong Church-Turing thesis. So the modern quantum information theory Church-Turing thesis, which is at the moment what people would conjecture to be true, is that any reasonable model of computation can be simulated by a quantum computer efficiently. We still believe the original Church-Turing thesis says nothing about efficiency, but if we care about efficiency, then there are some problems that can't be solved efficiently on a classical computer that can on a quantum computer. Okay, but the key point is that the quantum Church-Turing thesis says that once we have one model of computation, it's as good as any other model of quantum computation. Why does that say anything at all? How does that connect to physics in any way? Well, you get a flavour of it from thinking about what exactly is a quantum. Is this abstract quantum computer I've got, this circuit where I've got my quantum bits, my qubits flowing through this and being processed? Well, if you try and implement a quantum computer in reality, there's many different ways that people are trying to do this, but whatever you do, you're taking a bunch of quantum systems and making them interact with each other. There's attempts to do this using ions in ion traps, there's attempts to do this using photons, there are people working on doing this with superconducting circuits. But all of these involve taking some quantum systems and making them interact with each other. And it cuts both ways. If we have a bunch of quantum systems, a quantum system made up of a bunch of particles obeying the rules of quantum mechanics, then we can always think about that as carrying out some kind of computation. It's starting in some configuration, which we could just call the input, and at some later time it's in some other configuration, which is the output. In an abstract sense, it's performing a computation. It's computing its own dynamics, if you like. So actually computation and physics, if we really believe that computation is something physical, and Turing certainly did, then the Church-Turing thesis is actually asserting something much more than just saying we can take whichever convenient model of computation we like. It's saying that any process in the universe that we can think about it as a computation, and that the dynamics of that system will also, everything that we can prove about our circuits, quantum circuits, will also apply to those physical systems as well, or say something about those physical systems, because the physical systems are just doing some kind of computation as well. Okay. So I'm going to try for the rest of the talk to make that a bit more concrete. But the fact that another way of saying this is information is physical, which Landauer's principle coined that terminology, that information is not just some abstract thing floating around. Information is always some physical system in some state, and there is information and physics are actually the same thing. They're not. One is not some completely abstract thing divorced from reality. The Church-Turing thesis says something similar in another way. Okay, how does that let us say things about physics using the tools from computer science? So perhaps the most important result in this area was a result by Alexei Kitaev from around 2000. Kitaev is an interesting guy. He's Russian, he doesn't talk very much, and he doesn't publish very much, so most of his ideas are communicated by people writing them up because they need them to do their work, and then acknowledging Kitaev private communication in their papers. People in the field wonder if Kitaev is sitting on a whole stack of results that he just can never be bothered to write up and publish that would revolutionize the field. Well, we may never know, because he may never get around to writing them down. He's a genius, however. What Kitaev showed in 2000 was that there's a physical problem that's quite difficult, that is very important, which is to calculate the ground state energy of a quantum system. I forgot to say what the ground state energy is. So remember my energy diagrams? Ground state energy is just the lowest energy in that diagram, with the lowest energy the system can take. Given whatever system it is. So that we've seen why that energy is important, because if you cool it down, it'll end up with that energy, the lowest energy it can have. So Kitaev proved that calculating the ground state energy of a quantum system is a hard problem, even for a quantum computer. And hard here means what? Well, hard, roughly speaking, means even if you just take a system with a handful of atoms, in order to be able to compute its ground state energy, it would take an inordinate amount of time. Or if for 10 atoms you find you can compute with enough effort compute the ground state energy, then they'll give you a system with 11 atoms, and the time it will take will double. And it doesn't take me, I don't have to have very more atoms before there's no hope of you computing it. Now, let's be careful what this says. It doesn't say that this problem is always hard. There are some systems where you can compute the ground state energy. So some way you can do it on pen and paper. What Kitaev's result says is that there do exist some systems which you will never, in any reasonable amount of time, be able to compute their ground state energy. There are other systems where you can do it easily. Okay, is that clear? Yeah.
What about like a system for which you have an analytical solution?
Great, you do it with pen and paper, and that's an example of one that isn't. What Kitaev's result says is that the calculated ground state energy of the quantum system in general is hard, but for specific cases it can be easy. Yeah.
And so this is in general systems that you can't simplify using the Oppenheimer approximation or something like that?
Or any other more sophisticated tools where you can't use DMRG to solve them, or you can't use, there are systems there are many quantum systems there are some quantum systems where we can solve them, and we've got good techniques to compute things around them, but most of them we don't.
Can you describe one of the systems that is an example of
in some sense, yeah. But I don't think this is the answer you're looking for, really. But it's just a bunch of qubits interacting with each other by some Hamiltonian. I mean, if you construct, what Kitaev does is construct Hamiltonians. His original construction, they're very artificial Hamiltonians. You'll never see these in reality. You'll just see these on paper, unless you really try to actually engineer such a system in the laboratory. Okay, even that's rather far-fetched. They're very artificial. It's a mathematical theorem. People have subsequently, I'm going to talk a bit about this in the next slide, and subsequently there's been a lot of work to simplify the constructions to get it closer to systems you might actually encounter in condensed matter physics, say. So they're just artificially constructed systems, but it proves that in principle there are such systems where you can never calculate the ground state. So, yeah.
And now I was just going to ask, so like in real life, the systems that we encounter, you said, are somewhat easier. So those we can model, or?
Some yes, but many are not.
Yeah.
There's something called if you know about it, the Fermi-Hubbard model is conjectured to model high temperature superconductivity. We can't damn well compute its ground state energy or various other properties of the system. No one's managed to find a way of doing that, and so we don't know if that really is the right model or not. So there are many systems. In some sense, the history of applying quantum mechanics or studying quantum systems, condensed matter, particle physics, is the success stories where we were able to do these computations. But there are many ones where we're stuck, especially in condensed matter, for example. If you know any complexity theory, what Kitaev proved more formally is that this problem is a quantum version of NP hard, and that has a name called QMA hard. But if you don't know what that means, it doesn't matter. Okay. So the proof of this theorem No, I said no maths. So if you want to see the proof, you can come to my Part 3 Maths Advanced Quantum Information Theory course next term. It's a fantastic course. And the first eight lectures of the course are proving this theorem. Good. But what does that mean for us? I'm interested in what this is a result about doing some computation, and it says that this is a particular problem quantity you might want to compute, and this is a quantity that's can be hard to compute even if you have a quantum computer at your disposal. But wait a second, because if we this is about computing the ground state energy when I give you a mathematical description of the system. In principle, I could just go and build a system in the laboratory, right? And then I could cool it down. And then once I cooled it down, I could measure its ground state energy. And then, I would forget all of this mathematical nonsense of computing things on a quantum computer. I'm just going to build the thing, cool it, and measure it. This is a physical quantity. I can just measure the thing. Okay. The problem is, that runs into, but that has an interesting implication, because it says if the system does cool down quickly, well, we can do what I said. We find the ground state energy and measure it. But Cubitt proved that that's not possible. So there's only one possibility, right? So this contradicts the Church-Turing thesis, which says, because this cooling system down is a perfectly reasonable model of computation. Right? It fits into the Church-Turing thesis. It's a slightly strange model of computation, but it's a model of computation, and it should be equivalent to what Cubitt proved about quantum circuits. So if I could do this, it would contradict the Cubitt result plus the Church-Turing thesis. Cubitt result Church-Turing thesis would contradict the fact that I can cool the system down. And that indeed is the answer. The answer is that these systems, the energy landscape, cannot possibly look like that. It must look like this. It must be something that gets stuck. Because otherwise, if we could cool it quickly, then we would contradict Cubitt's theorem plus the Church-Turing thesis. So it must be one of these systems where as we try to cool it down, it gets stuck for a really long time in some metastable state here. And it takes a really long time to manage to get over that barrier and get to the ground state energy. And then we don't have a contradiction anymore. Because now it will take an exponentially long time to reach its ground state. And then we would be able to measure it and get the right answer.
But again, this is not for all of the systems. You can say there are systems that are like the ones on the left side, but there are some that are the ones on the right
And what if we put together Cubitt's results and the Church-Turing thesis, and what that tells us is that there exist systems that behave like glasses. They have a name, they're called spin glasses. It doesn't say that everything behaves like that. Right? Cubitt's theorem says that there exist some systems for which it's difficult, so the implication is that there do exist quantum systems that behave like this. But we've derived that from purely using computer science. We've used Cubitt's result, which is a result about computing quantity on a quantum computer. And we've used the Church-Turing thesis that asserts that any model of computation is equivalent to the one we're proving things about here. So without doing any physics, just using computer science, we've actually said something about there must exist systems with certain physical behavior. And it's actually rather important that what Cubitt proved was that it was difficult for a quantum computer, because cooling down a quantum system is clearly not a classical process, or we can't assume that it's a classical process. It's probably a quantum process, so it's equivalent to quantum computation. There's no reason to believe it would be equivalent to classical computation. So here we really need the fact that this is a quantum computing result. Okay, that's great. That sounds fantastic. But we already knew that spin glasses existed before this. Okay, so it's nice to reprove things we know in a different way. But it would be nicer to get something new. But I said that there was a long sequence of results that were taking Cubitt's result, and there's a whole subfield now of quantum information theory built on this called Hamiltonian complexity. And one of the results from that field is by a relatively recent result by Haranov, Gottesman, Irani, and Kempe. And what they did is they showed that Cubitt's theorem applies even if we have a system that's just a chain of particles sitting on a line. Even for systems where we restrict the form of the system to look like that. This is just an electron interacting with its neighboring electron, interacting with the next one along. Or some other linear system. They proved that Cubitt's theorem still holds for such systems. Okay? So there exist systems like that for which computing the ground state energy is a problem that even a quantum computer won't be able to solve quickly. Well, same argument as before. That now implies, same thing before, but now implies that one-dimensional spin glasses exist. That won't sound surprising to you if you're not a physicist, but physicists thought that was impossible. until this result. They had heuristic arguments for why spin glasses in one dimension couldn't possibly exist. Systems that there were no systems that were one-dimensional that got stuck in a metastable state, as you called them now. But this Haromov-Boston-Irani-Kempe result, together with Churchill thesis, implies that there do exist one-dimensional quantum spin glasses. And that was a new result derived entirely from thinking about physics as computation. So personally, I find it just remarkable that you can say anything about the behavior of a physical system just by showing that some problem is hard to solve on a computer. Okay, so far I've talked about the kind of area that is one of my main areas of research interest, but I haven't talked so far about anything that I've done myself. So in the very last part of the talk, I'm going to explain one piece of work that we've been doing recently that is really very much in this area that proves this kind of, uses computer science, theoretical computer science, to actually say something about physical systems. And for that I need to go back to do a little bit more physics. Remember my energy diagrams, my sketch of my Hamiltonians. I have two different types here that look rather different. So this one has a ground state, and then above that ground state it has a gap, and there's in the next configuration, up in energy is at some higher level with some gap in energy between them. Whereas on the right I have a system that's like an electron in free space. I've got the lowest energy level, but then it can take any higher energy, give it any small amount of extra energy that I like. So this would be like an electron confined to an atom, say, or this would be a system with an electron just moving about freely. Those are two different types of system with rather different types of Hamiltonian. We call that on the left, logically enough, that's called a gapped system, and one on the right is called a gapless system. Why do we care about that? We care about that largely for many reasons, but a lot of it is about phase transitions. So now I need to tell you what a phase transition is. You know what a phase transition is, so here's an example. If you heat up ice, it melts. There's a phase transition. But the crucial thing, the point of what is about a phase transition is that actually what happens more precisely is we heat up ice, and at some critical temperature it suddenly melts. Right? There's some precise temperature at any given pressure at which the ice at that precise temperature changes in a dramatic way from one state of matter to the other. So that's an example of what's called a classical phase transition, because it's a phase transition that undergoes a change in the state of matter when we change the temperature. There are also things called quantum phase transitions, which happen at zero temperature or a very low temperature. For example, here's a sketch, an example of the kind of thing you have, the kind of quantum phase transitions you see. So this is actually rather an important phase transition for this very ancient laptop. If you have some system of spins, which behave like, or basically spins in a quantum magnet, then if you have some low magnetic field, these spins might be all higgledy-piggledy. One is not aligned with its neighbour in any way. And so there's the overall magnetization of this, it all cancels out. But if you increase put it in an external magnetic field, and make that field stronger and stronger, at some point, these quantum magnets are all going to align, and you get some overall magnetization, because all of the magnets are now pointing in the same direction. Why did I say it's important for this laptop? Because this laptop is so old, it's still using spinning disks of rust to store data on, and this is essentially the phase transition that you use to store data in rust. I don't actually care about any physical details of what's going on. Here's the important point. A quantum phase transition is exactly, when does it occur? It occurs exactly when, as I change my system and my energy level, my energy landscape is shifting. Quantum phase transition occurs when the system becomes gapless. Okay, so as I change the parameters of the system, as I change the external magnetic field, these energy levels may close up. At the point where the system becomes gapless is where you have a quantum phase transition, and you have this sudden change in the state of matter. For a quantum phase transition, classical phase transitions are driven by different processes. Okay, so this is why we care about this particular property of the energy landscape, of the Hamiltonian of the system. It's because it characterizes quantum phase transitions. So we would really like to know given a system, is it gapped or is it gapless? Or as we change the parameters of the system, as I change the magnetic field, when does it, external magnetic field, when does it become gapless? Because then we know that at that point it's going to undergo a dramatic reorganization into a different state of matter. And that's captured by something called the spectral gap problem, which is just what I just said. So if I give you a description of a quantum system, or more precisely, I give you the Hamiltonian. So I give you something that tells you, given the energy of every possible configuration of the system. Tell me if it's gapped or gapless. Okay, it may sound like that's obvious. I've just given you the energy landscape, but of course you don't. In a model, you don't explicitly have the energies. You have a description of the system that says, okay, this particle interacts with that, and this particle interacts with that one in that way, and all that together forms the Hamiltonian, and you need to compute from that, the spectral gap in this case. Just as from that description of the system, you needed to compute the ground state energy in Kitayev's result. Okay, so from the mathematical description of the system, we want to compute the spectral gap, and that's the problem of mapping out phase diagrams of quantum systems, is trying to do that for a specific type of, maybe for a specific system you're interested in. Roughly speaking, that's about half of condensed matter physics is trying to solve this problem for specific systems. The other half is dealing with classical phase transitions, where you raise the temperature and see what happens, and that's different. Mathematics is different. This is a bit clear, of course, but it's a lot of condensed matter physics, like understanding the phase diagram of the model of think models, high temperature superconductivity. We need to solve this problem for that system. Here are some examples, special cases of this, the spectral gap problem. There's one that's you won't, unless you're a condensed matter physicist, you won't have heard of. It's called the Haldane conjecture, but it's a problem that asks exactly for a particular system called the Heisenberg chain: is it gapped or gapless? That problem has been unsolved for more than 30 years now. There's another one that you may have heard of, the Yang-Mills mass gap conjecture. This problem asks whether a particular model of high energy physics, is it gapped or not? Does it have a spectral gap or not? If it does, it would explain why quarks always come in pairs or in threes, or why you can't pull quarks apart. The point is, this is another problem. It's another special case of this general problem. And this has been open for quite some time as well, and not only that, but you would win $1 million if you solve it, because it's one of the Millennium Prize problems from the Clay Mathematics, Clay Mathematics Institute. So this is just to say that this is a very important problem, because even special cases of it are huge open problems in theoretical physics that we'd really like to solve. So we recently proved that this is hopeless in general. We proved that the spectral gap problem is an undecidable problem. I don't have time to tell you what an undecidable problem is precisely, but essentially what we proved was that we mathematically proved that this problem cannot be answered. Unfortunately, we didn't prove it for Yang-Mills theory yet, so we haven't yet won $1 million. But that's again, we proved that there exist systems for which this problem can never be unsolvable. But unfortunately, our tools don't extend, are not strong enough to prove it for Yang-Mills theory, or even to solve the Haldane conjecture. Those problems could still be solvable because they're special cases. But the general problem, give you a description of a quantum system: is it gapped or gapless? In other words, is it undergoing a phase transition?
If you prove that the Yang-Mills one is undecidable, do you still get the money? Or?
I don't know. To be honest, no, because there's two halves to the Yang-Mills Millennium Prize problem. Part one says, what is Yang-Mills theory? Part two says, having figured out what it is, can you now prove whether it's gapped or not? So if you look at the specification, actually no one knows even how to write down that Yang-Mills theory in a way that's mathematically precise enough to answer. So the first part of the problem is to write down a precise mathematical formula that people will accept as being the right one, and then prove something about it. So arguably it's the most difficult of the 7 Millennium Prize problems, because there's actually 2 really difficult problems in one. So yeah, there's not much hope of winning that $1 million. You never know. Okay, so how did we do this? I'll give you a short sort of flavour of kind of the ideas that go into this. It's really just a sketch, but I want to give you an idea of how yet again, what we did was to take computer science and apply that to this physics problem. So remember that Kitayev's result. Kitayev proved that computing the ground state energy of the Hamiltonian is of a quantum system. Computing the lowest possible energy can have, for some systems, is a problem that a quantum computer can't solve quickly. It can solve it eventually, but it can't do it quickly. What Kittov's result so what that does for us is it manages to connect computation to a quantum system of interacting particles. We use that construction, not the theorem, but the way he proved that, to actually manage to encode in some way a quantum computation into the structure of the system when it's sitting in its lowest energy level state, its ground state. And then we construct a quantum system, and we construct mathematically, so that it's gapped, it has a spectral gap. If the computation that is somehow modeled in the structure of the configuration of the system, if that computation actually just terminates, but if the computation runs forever, then the system doesn't have a spectral gap, and the gap closes. And those of you who are familiar with Turing's work, Turing proved that the halting problem, so deciding whether a computer program will halt or not, is an unsolvable problem. So we managed to show that the halting problem, the problem of does a computer program ever terminate, or does it run forever? We've turned that into something that determines whether the system has a gap or not. The halting problem is undecidable, therefore our problem is undecidable. Okay, that's the short version of the proof. The long version of the proof is 140 pages, which is still in preparation, and has been in preparation for a while, partly because there are 140 pages of it. Hopefully the paper should be out by the end of this year. I guess I put 2015 there. Hopefully it'll be to this 2014. Okay, that's one immediate implication of this, and one immediate implication of it is that it says that there exist certain quantum systems where whether it has a spectral gap or not, so this very physical property of the system, is actually mathematically undefined. You can take any set of axioms of mathematics, and I will be able to give you a system where the axioms of mathematics simply do not determine whether the system has a gap or not. That sounds very strange. Yeah.
Does this assume that anything you can prove in mathematics can be proved by a computer?
Yes, but so does that begs the question: what does it mean to prove something in mathematics? So you're a mathematician, if I remember right. Yeah. Okay, so let me do some maths for 30 seconds. If you have a proof, then is the formal system. So I can actually make that maths fundamentally is just shuffling symbols around according to certain rules. If you can shuffle symbols around according to certain rules, you can do that on a computer if you like. You can shuffle those symbols around on a computer. So taking that standard definition of what it means to prove something mathematically, which is to shuffle symbols around according to some rules to reach some string of symbols that are your theorem, then yes, it is assuming that, but that's the standard, that's what the definition of a proof is in mathematics. I don't want to say too much about this because this isn't where the main thrust of this talk. It does have the intriguing implication that at least it could be that this is what it means that these big open problems of physics, this opens the door to potentially proving that these are unanswerable. Who knows? Our techniques aren't strong enough to prove it for these specific cases, only for the general case. What I wanted to say is, what is this? This sounds very bizarre. I've got a physical property of a system that I could in principle measure, and yet I've just claimed that mathematics doesn't tell you what the value of that property is. It's undefined. What it actually, for real physical systems, what it implies is that there are systems out there that have physics behave in ways that are completely bizarre physically. I mean, they have perfectly well-defined behavior, but it's very strange physics that hasn't been encountered before, and this predicts that such systems with this strange behavior do exist, and could in principle be constructed in the laboratory. So one implication is that, remember the phase diagram. I had this phase diagram with ice, and as they change the temperature it melts and becomes water, or some magnetically disordered system where as I crank up a magnetic field all of the magnets align. What this result implies is that there are systems whose phase diagram looks nothing like those. Their phase diagrams look something like this. Where by this, what do I mean? I mean every white point here is a phase transition. However you change the parameters of your system, you change them a tiny little bit in any direction, it will undergo a phase transition to another state in every possible direction. And if I try and zoom in and see, okay, what's really going on in that region, it'll look just as complicated as before. And I zoom in further and it will look just as complicated. The phases of the system are so mixed together that it's undergoing phase transitions no matter how you move all the time. We've never seen something like that in physics, in actual, at least nothing quite like this, in real physical systems. What our result predicts, because if it didn't have this structure, the problem would be decidable and it would contradict our theorem. So it predicts, and we can even write down systems that, the models that have this proper behavior. If you could build this in the laboratory, they would have extremely bizarre physics that's new. And again, that's new physics that we're predicting purely on the basis of computer science, of the undecidability of the Halton problem. I'll finish with one last implication of this result. If you take that system and say, okay, let's take a sample of it in the laboratory and measure it. Again, the spectral gap is a physical property. We can in principle build the system and just measure it, and it has some value. The thing is that the system in laboratories always has some finite size. You can't take an infinite sample of the system. So if we take some finite sample, what happens to this, and we measure it? Well, the system has to have some value of the gap, so of the energy gap, so it has some value. Let's say it's gapless. It has no, the gap here is 0. Then we're going to take a slightly bigger sample of the system just to check. And we do all of our measurements again, we measure what the gap is, and it will be 0 again. What our results predicts for these, or improves for these systems is that at some point, if we just add one more row of atoms to our system, suddenly a gap will appear, and the value of this physical property will suddenly jump and change. And not only that, the size at which this happens can be arbitrarily big. It could happen in a size, 1 centimeter square. It could not happen until you take a sample of your system the size of the Earth. Or it could be, I can write down a system where this transition from having no spectral gap to the gap opening will happen only when you take something the size of the galaxy. Not only can it happen, can be arbitrarily large, because the behavior of the system changed just by adding one more row of atoms at some arbitrary large size, but the size at which it happens can never be computed as well. So again, this implies that there are systems out there, or in principle there exist quantum systems with extremely bizarre physics that's never been seen before. This is predicting a new type of behavior that no one had sort of dreamed of before. And again, we've proven that this can at least theoretically exist using tools from just using computer science. And the Churchill thesis that connects computing with physics.
What sort of implication does this have for material science, where, like, let's say you're simulating material, you assume that that properties change smoothly if you move atoms, and if you add new atoms on the end?
It means that in principle, you could manufacture a system where that's just completely wrong. There are some systems, again, this says that there exist such systems. It doesn't say that everything behaves like this. Clearly, many things don't. But it says that we could, in principle, manufacture a system that has the Hamiltonian view it comes out of our proof. And it would have this really bizarre behavior where this would be completely discontinuous, and it would suddenly, it would go from being, I don't know, I'm not enough of a physicist, it probably what I'm saying doesn't quite make sense, but it would go from being a conductor, and then you just add one more atom and suddenly it becomes an insulator. This is a long way from actually something you could ever build in a laboratory. Okay, this is a mathematical result. The systems that we come out of this proof are horrendously complicated. Nothing you will ever be able to build in reality. But they do in principle exist. And of course, this is just an artifact of our proof. Maybe much, much simpler systems also have this behavior. And indeed, that's one area direction we're thinking about. Okay, so I'm going to finish there. Hopefully I've convinced you that you get all of this very intriguing physics implications coming out from just knowing that quantum computers could exist. And nothing I've said, none of these results rely on actually ever building a quantum computer. They just rely on the fact that quantum computers can in principle exist theoretically, and that's all we need to be able to derive some very interesting physics from that. Or in other words, I really, really don't care if no one ever builds a quantum computer. My research will be completely unaffected, except that I'll probably use all of my funding. So I hope that someone does. So thanks a lot for listening for so long.